Hi everyone, welcome to lecture 1 of what's my personal favorite subject of all time. Yes, you heard that right. Differential equations and linear algebra. You could also call this continuous and discrete dynamical systems. We're trying to describe systems that change over time. Continuous refers to differential equations, where the system changes in a continuous way, where the variable, time, takes on, all real numbers. Discrete dynamical systems refers to systems that change over time, where time takes on, whole number values like 1, 2, 3, 4, 5, 6, etc. There is interplay between the two subjects, and that's another part of what makes it pretty interesting. Currently, this is early summer 2020. The coronavirus pandemic is going on. These lectures are meant for my class at Bethel University in fall 2020. Talking to you, my students personally, I don't know whether we're going to meet in person or not, so I'm trying to get a head start on things, trying to make some lectures to give us flexibility to possibly meet in person, but also possibly meet online. Lecture 1 is what is it all about? We want to get the big picture of things as well as some details, okay? And in pretty much every lecture, I'm going to try to have a time where you focus on working on a problem, and then also show you the solution. So we'll try to make it as interactive as we possibly can. All right, so what do you need for the textbook? Well, the main text that we use is a differential equations book by Blanchard, Devaney, and Hall, 4th edition. It looks like this. Okay, this is a differential equations textbook, not a linear algebra textbook, but I will say there's plenty of linear algebra in here. Okay, so be aware of that. Do I like this textbook? Yes, I do like it, otherwise I wouldn't use it. Now, you'll see online that some people don't like it. And it's true, it's not the best reference book. If you're trying to find examples, it can make it difficult sometimes. It is meant to be read, and I will tell you that I find that people who actually read it do like it. It's written in a very conversational tone, and the authors really try to get across the main points in a very intuitive way, in fact, okay? And they're even funny sometimes, so try to make sure you do that reading. There is some linear algebra in it, but maybe not enough to call it a differential equations and linear algebra class. So I'm also going to supplement with a book that I'm writing at my blog. My blog is infinityisreallybig.com. The linear algebra book that I'm writing online is called Visual Linear Algebra Online. Okay, here's a picture of my blog. Let's actually go there so you can see it. My blog has got lots of different things related to math. But if you go down far enough, you'll find along the right side a list of different topics, and one of those topics does include linear algebra. I've got 10 blog posts, which are essentially sections of my linear algebra book on my blog right now. I'm going to write more over the coming months. The last section here, which I wrote almost a year ago, August 29th, 2019, is about the determinant of a matrix. There's stuff about matrices and matrix multiplication, high dimensional linear algebra, vectors, something called linear transformations as you keep going on down. And in fact, the very first section of the book is about something that seems pretty simple. Points, coordinates, something called skew coordinates, and their graphs, which sounds like that might be too basic to even bother reading, but don't give in to the temptation to think that you don't need to read it. You should read it. There are a lot of subtleties with even basic things that are worthwhile to learn in this subject, to really understand more fully what's going on. Now, these sections are not super short. These are pretty long blog posts, and the reading will take a while. The reading is a big part of this course. You want to make sure you do it to really understand things. Okay, so that's something that you should do, and I will continue writing and hopefully adding more sections here as the summer moves on and into fall 2020. What is our main goal for the course? Okay, so this is a statement that you should keep in mind as we go through the course as, our purpose. This is like a purpose statement. And what is it? I'm describing it this way: to quantitatively and qualitatively model, describe, hopefully understand, and hopefully predict the behavior of various quote-unquote systems that change over time. Dynamical systems, or some people say dynamic systems, are systems that change. The word dynamic means change. We want to quantitatively, with numbers and with formulas, and qualitatively with graphs and, say, verbal descriptions, model something hopefully accurately about the world, describe it, use words to say what you see in the graphs, for example, understand. Do we really understand it? Well, we hopefully will at least understand the math, even if we don't understand all the implications for real life. And then make predictions. Use the formulas, for example, hopefully to make predictions about the future for these systems that change over time. What are the typical kinds of behavior that we're going to see in these systems? Well, one kind of behavior is actually very simple. You might call it static behavior. Essentially, it's something that doesn't change over time. You could represent that with, say, a horizontal graph, a horizontal line, a function that doesn't change over time. That would be a one-dimensional way to think of it. We will also be talking about things called phase lines, phase planes, and phase spaces. And in that situation, a static version of this horizontal line is actually just a single point. When you think of that one point as a constant parametric curve, which is not really a curve then if it's just one point, but that's one way to think of it. Other kinds of behavior we'll see are exponential growth, for example, exponential decay, oscillatory behavior, maybe with a constant amplitude, maybe not, maybe the amplitude decreases over time, and maybe chaotic behavior like with the Lorentz attractor, kind of unpredictable, sort of up and down for a while, then maybe up and down for a while over here. Things that can be pretty hard to predict, even within deterministic systems like the Lorentz attractor. That was the big reveal, that in deterministic systems, unpredictable kinds of things can happen. Chaotic things can happen. The butterfly effect really is a real thing. How will we do this? In a nutshell, you could describe it as saying, by working from local to global. Local to global, what does that mean? In math, it means, think about the little pieces, local pieces, like of a graph, for example, and piece those things together to get a bigger graph, a global graph. That would be just a way of thinking about local to global with graphing, but we could also think about integrating. Take the values of the derivative, integrate them, you're going to get the change in the original function. That's the essence of the fundamental theorem of calculus. Here's something called the infinity principle by Stephen Strogatz from this book here, Infinite Powers, which I highly recommend, and in fact I'm going to put an Amazon link to it in the description below, that describes this in a way better than what I just said. Here it is. To shed light on any continuous shape, object, motion is going to be a big one for us, process or phenomenon, no matter how wild or complicated it may appear, reimagine it as an infinite series of simpler parts, analyze those, and then add the results back together to make sense of the original whole. So we're going to see this come out in examples. In a word, this is essentially integration. However, and this is really good, it does not always involve actually doing integrals. Sometimes it will, and in fact, here early in the course especially, it will. But other times, it won't actually involve doing integrals. And that's actually a good thing, because it'll save us some time. Integrals in general can be a pretty hard thing to do. What are our main applications for the course? Population growth and decay, including interacting species, which we'll talk about at the very end of Lecture 1 here briefly today. Projectile motion, with and without air resistance. The simplest form of projectile motion is just up-down motion under the influence of gravity. A little bit more complicated is two-dimensional motion, like a projectile following a parabola. Financial growth and flows. So we'll talk about compound interest and what happens when you maybe do more than just let your money sit in the bank, but you also, say, continuously add money. Heating and cooling. We'll talk about the basics of that. That's called Newton's law of heating and cooling. We could get into more depth with something called the heat equation. Maybe at the very end of the course we'll have a little bit of time for that. Mixing problems, more officially called compartmental analysis. That sounds fancier. Essentially, we're talking about say, mixing some salt water with some pure water to get some sort of mixture, and we're wondering what's the amount of salt in the mixture as a function of time, and we'll make some simplifying assumptions there so we don't have to worry about spatial effects. Big thing though is actually harmonic oscillators of various forms. Maybe you've heard that phrase before, harmonic oscillators. Essentially those, well, in the simplest case, are things that follow oscillatory behavior like a sine wave or a cosine wave. The general name for that is sinusoidal wave. Mechanical and electrical. Mechanical means like a mass on a spring, say moving up and down. Electrical could mean, say, varying voltages or currents. Undamped and damped. Undamped means there's no friction, for example. Damped means there is friction. Linear and nonlinear. Linear is certainly the simplest kind, and when you think about, say, a mass on a spring, that does generally follow a linear model as long as you don't yank the spring too far, at least. Nonlinear, that comes up in another very common situation to think about. It's called the pendulum, something that swings back and forth like this. That's actually a nonlinear system, though it can be approximated by a linear system. And forced and unforced. So if you've got a mass on a spring sort of going up and down like this, and say it's attached to a piece of cardboard up here or something, if you move the cardboard up and down with your hands, that's one way of bringing forcing into the system, and that will obviously affect what happens. And unforced, you're not doing that. Here's an example. An unforced, undamped harmonic oscillator. So what I'm going to show you here is a graph. And with the graph, you're going to see a dot moving up and down. What you should imagine is that dot is, say, a mass hooked to a spring. Now, I didn't actually draw a spring in the picture. It's just a dot moving up and down. But it's going to follow a cosine wave. And that's an example of a harmonic oscillator, sometimes called simple harmonic motion. It's about as simple as it can be with oscillatory behavior. That's a solution, actually, of a differential equation. What is the differential equation that this solution satisfies, as well as some initial conditions? In other words, an IVP, or initial value problem. Here it is. The second derivative of y with respect to t twice equals -4 times y. That's the differential equation. These two equations are the two initial conditions, I should say. Y of 0 equals 1, and y prime of 0 equals 0. Let's focus on the initial conditions first. That's easier to think about here. Y of 0 equals 1. The value of this function, this red graph that you see here, at t equals 0 is 1. That point right there is a point on this graph. It satisfies this initial condition. Y prime of 0 is 0. The initial slope, rate of change of this red graph at t equals 0 is 0. The tangent line at that point right there is horizontal. So it's fairly easy to see that these two initial conditions are satisfied. What about the differential equation? What is that saying? It's saying that no matter where you are, no matter what time you're at, now this is moving here, so we can't always focus on the particular time in general. And there's a reason I wanted to move it here to show you the actual motion, again, of this up-down dot here. At any specific time you pick, there's a certain point on the graph. You know, this point looks like it has coordinates. Maybe t is about 0.8 and y is about maybe about 0.18 or something like that. The second derivative, which tells you about the concavity at that point of this graph, is equal to -4 times the y coordinate of the point. -4 times 0.18, which would be -0.72. That is the second derivative of this graph, approximately, at that point. Now, that's not such an easy thing to be confident of in looking at the picture, other than to say it does seem reasonable that it should be negative. The graph, in fact, is concave down from t equals 0 to t equals right about there. Okay? So other than the fact that it's negative, it's difficult to say that that really should be the case, that the second derivative of this graph at this point should be -4 times 0.18, which again is -0.72. But that really is the case. And that happens not just at this point, but at all the points. How is this related to a mass in a spring? Well, essentially, if you imagine the mass to have a mass of 1 kilogram, you can think of the second derivative as, say, 1 times the acceleration of the object. If y is the up-down position of that red dot over there, as time goes by, which you can see in the animation there, that would be its acceleration. When the second derivative is negative, when the graph is concave down, the acceleration is actually negative. Which can be confusing here, because it should seem like this dot is speeding up as it's moving downward here. And in fact it is. However, it's speeding up in the negative direction. And that's enough to say that the acceleration is negative there. Where else is the acceleration negative? In here, for example. Wait for it to come back around, about like that. The second derivative is also negative. In this part of it, it's moving in the positive direction, but it really is slowing down in that case. And in fact, right at that point, which evidently is at pi, the instantaneous velocity is 0. The slope of the tangent line is 0 there. So it's really slowing down in that case. It's moving in the positive direction. The negative acceleration in that situation means that it truly is slowing down. So you can make sense out of this as a mass times acceleration. What would this be? This is essentially a force. Now it doesn't look like a force, does it? Or it's not written as an F, and how can negative 4y be a force? We'll get into that later, okay? I think I'll leave that for the moment. What is the formula for this function? In fact, it is cosine of 2t. Maybe you guessed that already. This is a cosine function. 2t means the period of this is pi. It comes back to where it started when t is pi. This indeed is pi right here. How can you check that this is a solution? You can check that it satisfies the differential equation and the initial conditions. Let me do that on the board over here. Let's check the initial conditions first. So y equals cosine of 2t. Y of 0. By the way, I am kind of abusing notation here. This is a common thing to do in differential equations. I'm using both y for the dependent variable name and for the function name, essentially. That's something that our textbook does quite often. I will make some distinctions there in coming lectures that emphasize that that's actually a bad thing, though we won't typically worry about it. But it's something that you should be aware of. Y of 0 is cosine of 0, and cosine of 0 is indeed 1. So we satisfy this initial condition. What's y prime? The derivative of cosine of 2t will be negative 2 sine 2t. Right? Chain rule there. What's y prime of 0? That would be negative 2 sine of 0. But sine of 0 is 0. We satisfy the initial condition as well. What about the differential equations? This is the most confusing thing for people. How do you verify that this satisfies the differential equation? What you need to do is you need to take this function and substitute it into both the left-hand side and the right-hand side, and in each case simplify and see if you get the same answer in the end. So the left-hand side, LHS, is the second derivative. I wrote it in Leibniz notation here. For short, I'll just write y double prime. I already know y prime is right there. What's y double prime? Take the derivative of this, you'll get another factor of 2, you'll get negative 4 cos 2t. That's what the right-hand side simplifies, the left-hand side simplifies. What about the right-hand side of the differential equation? Negative 4y, what does that simplify to when I plug in this function? It simplifies to the exact same thing, negative 4 cos 2t. We have a match right here. These two functions of t are the same. They are equal for all values of t. That is the thing that you need for it to be a solution of the differential equation. This is a difficult thing for people when they're first learning about differential equations. Trust me, I've taught this course many, many times. Actually, mostly as just a plain differential equations course and not linear algebra. This is a tough thing for people at first. If you're confused about what I did, watch the last couple minutes again. Although I will summarize it. You take the function that you think is a solution, or you hope is a solution. You plug it into both the left-hand side and the right-hand side of the differential equation, and in each case, simplify and see if you get the same function of t in the end. Okay? And if you do, that means it's a solution over whatever values of t it's defined for. What are our main methods for this course? Our main methods include some specialized techniques for what are called separable and linear equations and systems of equations. Pretty quickly here, near the beginning of the course, we're going to use something called the method of integrating factors. That's the main spot where we'll be doing integrals, in fact. Later on in the semester, we're going to be looking at a method involving something called eigenvalues and eigenvectors. We'll do some educated guessing. Seriously, I'm not lying there. We will, and it will be really useful. And you will be able to do the educated guessing once you practice enough. It also tends to work better for linear equations. One big theme of the course, linear equations are nice, relatively simple. Nonlinear equations are not so nice, kind of hard, but sometimes we have to deal with them. This educated guessing definitely works better for linear equations. More officially, the method there of educated guessing is called undetermined coefficients. Here's the biggie, okay? And this is something that Blanchard, Devaney, and Hall emphasize a lot, and I'm going to emphasize a lot. We're going to use what are called qualitative techniques, not quantitative. Although it will still involve doing some calculations, just not as many as you could do if you were trying to literally solve for the solutions as formulas. These qualitative techniques can be described as phase plane analysis using something called null lines and something else called linearization. Now, you probably have no idea what that's about. Don't fear, we're going to get into it plenty, okay? We'll talk also about numerical approximation, in particular something called Euler's method. That is important. There are better approximation methods than Euler's method, but it's not really going to be the main focus of the course. It's worth talking about to some degree, and lots of people need those methods. They're really important, but it's not going to be our main focus. Our main focus is going to be on the biggie here, qualitative techniques. And then at the end, something called Laplace transforms will be another main method. How does linear algebra play into all this? Here's a big picture description. Linear algebra supplies both notation, like for vectors and matrices, and methods, like computing eigenvalues and eigenvectors, to conceptualize, represent, solve, and approximate differential equations and their solutions. That was as thorough of a one-sentence description as I could think of here. Conceptualize means that some systems are linear. It's a way to think about them. Represent, okay, that we're using the symbols, vectors, and matrices there. And when we solve, we'll use eigenvalues and eigenvectors, and we'll represent the solutions using vectors as well. Approximate differential equations and their solutions. That's the linearization piece when I mentioned the phase plane analysis with no lines and linearization. Linearizing nonlinear equations is a way to approximate their solutions. That's a real big deal. Okay, here's a summary of what I just said. Vector and matrix algebra to represent systems of differential equations and difference equations. I don't want to forget about difference equations. The biggie, linear transformations to represent, okay, here's the big thing, of course. Changes of coordinates. You could also call that changes of variables to facilitate calculations and understanding. Especially changes to coordinates defined by special vectors called eigenvectors and some numbers related to those called eigenvalues. This is a real big deal, and it's the main thing in my visual linear algebra book on my blog, Infinity is Really Big, it's the main thing I emphasize overall in chapter 1. Again, linearization of nonlinear equations to approximate their solutions. This one sounds kind of weird. Differential linear operators and spaces of solutions. If you've learned enough linear algebra in the past to have learned about vector spaces, that might give you a little hint about what this is, and linear transformations. Essentially, we want to use some linear algebra tools to describe solution spaces, which essentially consist of all possible solutions of a certain differential equation. More detail about that later. Not sure if we're going to have time for this last bullet. I'm hoping to. Something called inner product spaces. If you've ever heard of dot products, inner products are a generalization of dot product. Least square solutions and their relationships to solutions of what are called partial differential equations. Again, I'm not sure if we're going to have time for that. I'm hoping I will be able to fit it in. It's June right now. By November, December, hopefully I'll be able to make some videos about that. Partial differential equations involve partial derivatives instead of ordinary derivatives. They are harder to understand than ordinary differential equations. Some very famous ones we want to understand the basics of, something called the heat equation, the wave equation, and Laplace's equation. Hopefully we can get a little glimmer of what those things are about, but we won't be able to get into much depth. They are related to linear algebra, though. All right, now we're going to talk about an example. Okay, so that's the summary of everything. Let's get into an example here. And for this example, I will go ahead and work on it on this particular screen here. And then I think I have the solution. Well, I forget if it's on this screen or the next screen. Then I'm going to pause and let you work on an example. You should pause the video then. Here we go. Modeling. By the way, that says those wily rabbits. Okay, and there's a little bit of relationship to Elmer Fudd and Bugs Bunny there, if you know what I'm talking about. Modeling, describing, understanding, and predicting. Remember our big theme. Here's the situation. An unconstrained population of rabbits starts with 2 young bunnies and doubles in size every month. Does that really happen? I don't know, I just made it up. Actually, I did do a little bit of looking into how fast rabbits reproduce. And this is actually maybe not too far off the mark, at least in unconstrained situations. Our goal here is to represent this mathematically and determine when the population will reach 1 million rabbits. Would that really happen? Would it really reach 1 million rabbits? Probably not in real life, okay? This is unconstrained, so we're making an assumption here that's probably not realistic. In real life, there are constraints on food, constraints on space, constraints on people who might hunt those bunnies, sorry. So there are constraints, so this probably would not happen in the wild. And this is what happens with model building, is you start simple and see what happens. And then you say, that's probably not realistic. It might give us good approximations in the short run, but not in the long run. So then you tweak your model, you try to make it better. Okay, that is the process of model building, which is a big thing to do in this course. That's part of our main theme in the course. So let's go ahead and start describing this mathematically. I'm going to go ahead and use notation that you're going to see in later slides here. This is not obvious notation to use, but I'm going to go ahead and do it. I'm going to write P initially here to represent population. And I'm going to use a subscript n here. And I'm going to call this P sub n when I look at P sub n. And this is common notation in math for what's called a sequence. And a sequence, from one point of view, is just an infinite list of numbers that often has a pattern, like 1, 1/2, 1/4, 1/8, 1/16, 1/32, etc. That would be an example of a sequence that goes on forever with a pattern you keep multiplying by 1/2 to get the next term in the sequence. By the way, these are quotes if you can't tell what those are. P sub n. Technically speaking, sequences are more than just a list of numbers. They're really functions. In this notation, the n, the subscript, is the input for the function. It's the independent variable. It's the time variable. And the p, you might say, or maybe the entire symbol p sub n, is the dependent variable. And this is where we get a little funny with our abusing notation here. Is p sub n a variable or is it a function? We don't usually worry about the distinctions, the subtle distinctions between those two things. Sometimes we will, but not usually. What does it equal here? Essentially pattern recognition. So there's 2 bunnies at time 0, say. We can make a little table here. At time 0, we've got 2 bunnies. At time 1 month, look at the units here. This is every month. We're going to have double that. We're going to have 4. 2 months after the beginning, we're going to double again and get 8. 3 months after time 0, we're going to double again to get 16, etc. Essentially, we're after pattern recognition here. The number of bunnies is 2 at time 0, 4 at time 1, 8 at time 2. These are powers of 2. Is it 2 to the n? You could try it and see if that works. Is that right? When n is 0, this is time n here, you get 2 to the 0, which is 1, not 2. Okay, this doesn't quite work. Well, but a little adjustment will make it work. I can multiply this by 2. Now at n equals 0, I'll have 2 to the 0, which is 1, times 2 is 2. When n is 1, I'll have 2 to the first, which is 2, times 2 is 4. When n is 2, I'll have 2 squared times 2 is 2 cubed, or 8. This is looking like it's working. And you also could use rules of exponents to write this as 2 to the n plus 1. We can add those exponents. There is a very succinct mathematical description of what's going on here with the bunny population. Okay? So we have done the describing, mathematically at least. Is there other describing we could do? Yes, we could make a graph, and we'll see a graph here soon. Are we understanding it? Yeah, I mean, this is a pretty simple thing to understand. Can we use it to predict? That's what we want to do now. Represent it mathematically and determine when the population will reach 1 million rabbits. Now we're doing the predicting. Doesn't mean the predicting is accurate. It just means we're doing predicting. So essentially, it's just doing some algebra here. So I want to set p sub n equal to 1 million. This is a setting equal to, I'm not saying this is true for all n. I'm saying it's true maybe for some particular n, and I'd like to find that n. And if you think about it, actually, probably not a whole number here. So I need to solve this equation for n. Hopefully, from your pre-calc days, you know I gotta use logarithms, right? Doesn't matter what log you use. Could I use common logarithm, log base 10? Sure. Could I use natural logarithm, log base e? Sure. Could I use some other log base 2 perhaps? Would that be a good idea? Well, yeah, you could, but most calculators don't have a log base 2 button. So what would you do in that case? Well, maybe you would figure it out in some other way, or maybe your calculator does have a log base 2 button. Let's use ln. Okay, let's take the natural log of both sides, ln. That will be the thing we typically do. Log base e. That's going to imply natural log of 1 million is natural log of 2 to the n plus 1. Now, you remember all those rules of logarithms that you used back in pre-calc? Hopefully, and maybe you didn't like them very much? Well, now they're really useful, okay? You don't want to forget your rules of logarithms. In this case, you can bring that exponent down in front of the logarithm. You can write this as n plus 1 times natural log of 2. Actually, I think in my written solution, I had the function like this, and I divided both sides by 2 first, but we'll get the same answer here in the end. We'll see the written solution soon here. We want to solve for n. Even though this equation looks complicated, it's actually, conceptually speaking, a fairly simple equation in n. It's linear in n. I can solve for n by isolating it. First, divide both sides by natural log of 2. That'll cancel the natural log of 2 over there, and you'll be left with just an n plus 1. Then subtract 1. It looks like n is natural log of 1 million divided by natural log of 2 minus 1. You may want to get your calculator out, and oh, I forgot my calculator. Okay, I'm out of your sight here, but I'm going to use my computer to do the calculation here. Although my computer seems to be stalled. Oh no. Here we go. What is this approximately? I get approximately 18.9. I hope I didn't make a mistake there. By the way, I do make plenty of mistakes, so I'll try to catch them before I post it on YouTube here. I'm getting about 18.9 here. Maybe I made a mistake. But wait a minute, n needs to be a whole number. When the population will reach 1 million or higher for the first time, for the first value of n. So you really should round this up to n equals 19. And by the way, you would round that up to 19, even if this was an 18.1. Don't round down to 18. I mean, you could say it's approximately 1 million when it is 18, but to just get over 1 million, we want to go to 19. Okay, so we've made a prediction. Again, it's not clear whether that's accurate. Because by the way, that's 19 months. That's just a year and 7 months, a little over a year and a half. Yikes, to go from 2 to 1 million bunnies. Ooh, we better hope this is not accurate. All right, here I'm going to talk about that with some details that I already had typed ahead of time. That, by the way, was a difference equation, not a differential equation. It was a difference equation. It didn't involve any derivatives. Differential equations involve derivatives, like with a harmonic oscillator. This equation right here, P sub n plus 1 equals 2 times P sub n, where n is 0, 1, 2, 3, etc., is called a difference equation. Now you might scratch your head and wonder, why is it called a difference equation when there's no differences in it? Well, sometimes people write it with a difference. It's equivalent to, if you subtract 2pn from both sides, you get this. And there's a difference. So that might be one reason to call it a difference equation. Maybe it's not a good enough reason, but we'll go with it. It's also known as a recurrence relation. That's another name for it. Pay attention to what I say here. In a somewhat indirect or local way, remember our theme of going from local to global? It describes the rabbit population, Pn, as a function of the number of months n. How? It's saying to get the population in the next month, n plus 1 is the next month after month n. Take the population in month n and multiply by 2, double it. This is a local thing because it's focused on a particular value of n. Maybe n is 7, I know p sub 7, I multiply it by 2 to get p sub 8. It's local. However, we can pretty go easily to a direct or global formula. In fact, I wrote it on the previous slide. P sub n equals p0 times 2 to the n. For n equals 0, 1, 2, 3, dot, dot, dot. This is supposed to be a dot, dot, dot. And going from a Mac to a PC, it sometimes goofs it up like that. I need to remember that that happens. Wait a minute, this doesn't look like what I wrote before. What did I write before? I wrote a 2 there before. P0 is the initial population. There were 2 bunnies at time 0. So there was a 2 here before, but in general, there might not be 2 bunnies. There could be 8 bunnies, for example, at the start, or 10 bunnies even. Not necessarily a power of 2. P0 is the initial population. You see how this is a global formula? It's going to give you the answer if you know P0, or P naught for short, naught meaning N-A-U-G-H-T is sort of shorthand for 0. If you know that initial population, for any n, this will give you the population. You can plug in n equals 1,000,000. 2 to the million times P0. That's way too big, but. Whereas if you're using this form, you'd have to use this equation over and over again 1,000,000 times to get p million. This local equation can be easily solved to a global equation that's a better form of a way to represent the solution, a way to represent the population. This is better. The solution is better than the difference equation. Likewise, for differential equations, the solutions, if we can find them, are better than the differential equation in some ways, at least. Okay, here we come back to verifying it. Remember what I did in the board, but I erased over there? How do you verify this is a solution of the difference equation? Just like with the differential equation that was on the board, we want to substitute it into the left-hand side, LHS, and into the right-hand side, RHS, of the difference equation, to see if it simplifies to the same thing as a function of n. For the differential equation, it was a function of t. So, what does that mean here? The left-hand side is Pn plus 1. This is the difference equation up here. Pn plus 1. What is Pn plus 1 when we use this formula, when we use this proposed solution? Well, just replace the n with n plus 1. That's what I did here. I replaced that n with n plus 1 because there's an n plus 1 there. Okay. And what about the right-hand side? Oops, there we go. Right-hand side, that's this. 2pn, right there. What's pn? I'm assuming it's this. Plug that in there. It's right there. Simplify. Use rules of exponents. Get this. Hey, this thing and this thing are the exact same function of n. Done. That's why it's a solution of the difference equation. Okay, and again, I'll reemphasize this is something that people often have a hard time with at first when they're in this course. Learning about differential equations or difference equations is realizing what you're supposed to do to verify it's a solution. By the way, if you write down some arbitrary function of n, in all likelihood it's not going to be a solution. In fact, if you can't put it in this form, you can even prove it won't be a solution. Like I could write Pn equals n squared or something. Then Pn plus 1 would be, the left-hand side would be n plus 1 quantity squared, whereas 2Pn is going to be 2n squared, and these are not the same function of n. Not the same. I mean, they might be equal for 1 or 2 values of n, but they're not the same function of n. Therefore, that's not a solution of the difference equation. You should be able to verify other functions are not solutions. Okay? And you think of some other function that cannot be put in this form, it will not be a solution either. So that's really important. I'm going to keep emphasizing that. What do graphs look like? Technically speaking, for this difference equation and its solution, Pn, n is a whole number starting with 0, say, non-negative integer, is another way to say that, 0, 1, 2, 3, 4, etc. Technically speaking, I do not plug in fractional values of n, like a half or pi or 2.34 or something. And so technically speaking, I should make just some points and not connect the dots. That's what I did here, but I did add some lines to the picture. Some vertical lines at n equals 0, 1, 2, 3, and 4, and some horizontal lines showing you the outputs of this function. When n is 0, the output there is, that's a 2. This point has coordinates 0, 2. This line is at an output of 4. This point has coordinates 1, 4. This is an output of 8. This is 2, 8. This point here is 3, 16. 4, 32, and 5 64ths, 5, 64. There's a graph of this, and don't connect the dots. Now it's real tempting to connect the dots, isn't it? But don't, not for this kind of difference equation. Because we're not imagining this is necessarily accurate in between these whole number values of n, even though the formula could be accurate there. And in fact, when we think about a differential equation, we will assume it is accurate, actually. Here's another graph of it. It's various graphs. What did I do here? I made the scale in the vertical direction a lot different, and I also expanded the scale in the horizontal direction. I go up to n equals 20 here. And look, by the time you get to n equals 20, the output is up above 1 million. 10 to the 6th here, that is 1 million. And we are slightly above 1 million there. Okay. Here you can see more of the exponential behavior. This is an exponential function of n. It's not so clear here, other than the fact that it's increasing and concave up if you did connect the dots with the smooth curve. But with exponential functions, when you graph on a bigger scale like this, you're often going to see this kind of behavior. It seems almost horizontal for a while, and then all of a sudden it goes way up real fast. And if I made the scale even bigger, it would be even more pronounced. Same function, different labeling for the axes, does result in a different looking graph. One more graph I'm going to make is kind of weird. This. What am I doing here? It's the exact same function, but wait, it doesn't look exponential anymore. That's because I've essentially made the vertical scale logarithmic. You heard of log plots before? That's what I've essentially done here, although to technically make it logarithmic you'd focus on the exponents of these things. 10 is 10 to the first, 100 is 10 squared, 1,000 is 10 cubed, etc. And maybe you label these things with the exponents of the 10 instead. But essentially it's logarithmic. And this is actually a pretty useful thing. If you draw a logarithmic scale and you get data that is linear looking, it's actually an exponential function. Okay, I'll let you maybe think about why that's the case. Why am I doing this? Well, other than just to me it's kind of fun. I'm trying to emphasize a point I'm going to make real heavily in lecture 2, that graphs are not unique, for one thing. We can widen the window. But for another thing, we could change how the scale happens. And that is related to changes of coordinates, which I said was the biggie for how linear algebra is useful. This is actually a nonlinear change of coordinates in a sense because it's a logarithmic scale. But there are plenty of linear changes of coordinates that are going to be really, really helpful for us. I'm just trying to make an early point about that. Okay, now you try it. This is the point where you're going to try this. So you got an unconstrained population starting with 2 rabbits, triples every month. So there's the key difference, tripling instead of doubling. Represent this mathematically and determine how long it will take to reach a population of 1 million. Also write down the difference equation that this discrete function satisfies. So you should pause the video now and take the time to figure this out, mimic what I did a few minutes ago. And then I'm going to show you the answer. Yeah, so go ahead and do that right now. All right, now we're going to look at the answer. This is, again, something we're going to try to do pretty much every lecture. I will sometimes split these lectures into 2 pieces as well, but at least for these first couple, I want to do it all at once. So let's show you the answers. Here's a mathematical representation and a prediction of how long it will take. What's the difference? Pn is now p0 times 3 to the n instead of 2 to the n. However, if we are starting with 2 rabbits, we are still starting with 2 rabbits, p0 is still 2. But now I cannot combine these. I do not get 2 to the n plus 1 or 3 to the n plus 1. I get 2 times 3 to the n. And by the way, order of operations, if you're plugging in a number for n, make sure you do the 3 to the n first, then multiply by 2, right? Exponents before products. And again, this is kind of just a typo in going from a Mac to a PC. That should be a dot, dot, dot right there. There is our global solution of a certain difference equation. I didn't write down the difference equation. To figure out when it passes 1 million, set this equal to 1 million, solve for n. Here I did divide both sides by 2 first. Then take the log of both sides. Use a property of logs that this n would come in front to get an n times natural log of 3 equals natural log of 500,000. Divide both sides by natural log of 3, get about 11.94, round up. N equals 12 is our solution for the first whole number value when we get above 1 million instead of, what was it before, 19, I think, when it was doubling every month. So within a year, it's going to be above 1 million if it's tripling. Again, not necessarily realistic. What's the difference equation? It's tripling every month. You should have written down that Pn plus 1 is 3 times Pn instead of 2 times Pn. Right there. Is this thing here a solution of that? Yes, it is. I'll leave it for you to check. In spite of the fact that there's a 2 there instead of a 3. It does still satisfy this difference equation. The 3 there is what matches the 3 there. The 2 here is irrelevant. In fact, the 2 could be any number. It could be 5, it could be 10, it could be 100. The P0 doesn't matter. Let's move on to a continuous model. That was discrete. We were just talking about discrete dynamical systems there in those difference equations. And in fact, it was a linear difference equation because the Pn plus 1 equaled a constant times Pn. We're not raising to any powers. This is going to be a continuous model. It's going to involve a differential equation. You look at the description here, and it seems pretty similar to what we did before. An unconstrained population of rabbits starts with 2 young bunnies and doubles in size every month again. Here's the key initial difference. Pretend that the population can include fractions of bunnies. Obviously, it can't. Pretend. That's something you have to do in mathematical modeling a lot. Represent this mathematically and determine when the population reaches 1 million rabbits again. How do things change? The only way things change here, but compared to the previous example, the discrete example, is we think of the exponent, the n, as a continuous quantity, a real quantity, instead of a non-negative integer. It's really the same formula. To emphasize, though, that the variable is continuous, I'm going to call it t instead of n. And I'm actually going to write it as p of t instead of p sub t. And that will be something standard we do. We'll think of the subscripts typically as whole numbers. We'll think of letters that go in here as variables that are real numbers. But it really is the same kind of formula as before. And to figure out when it equals 1,000,000, we do the exact same calculation as before. And solve for t, and we get t as, if we didn't make a mistake, 18.9 or whatever it was. And we would not round, because we're after a real number solution. 18.9 months or whatever it was, that'd be like 18 months, and then 0.9 of a month is 9/10 of a month, which is about 27 days or so. And you could get it down maybe to the nearest, you know, hour, minute, second. Is that really right? Probably not, but it's sort of like the best thing you can do given the information you have. What kind of equation does that function satisfy? P0 times 2 to the t. If I think of t as a continuous variable or a real quantity, it satisfies a differential equation. Not a difference equation, but a differential equation. Differential equations involve derivatives. Differential essentially is, you know, synonymous with derivative equation. What is the differential equation? Well, let's figure out what the derivative of this function is. Remember with the harmonic oscillator example, we had a second derivative involved, and we needed to take the second derivative to verify it was the solution. So maybe we want to take the derivative of this and see what happens. You remember how to take the derivative of something like this? If that were an e to the t, the answer would be itself. It's a 2 instead of an e. When you differentiate something like that, you need an extra factor of natural log of 2. There it is. P prime of t, or dp dt. There's our prime notation, there's Leibniz notation. You should feel comfortable with either one. Gets an extra factor of natural log of 2. 2 times p0 2 to the t, which is really natural log of 2 times the original function for any real number t. I said non-negative real number. It even works for negative real numbers, but I'm trying to think about going forward in time here. This is essentially a verification that p of t satisfies a differential equation. Its derivative is natural log of 2 times itself. Say that again. Its derivative is natural log of 2 times itself. It satisfies this differential equation. dp dt equals natural log of 2 times p, which, since natural log of 2 is approximately 0.693147, we could also say the differential equation is approximately dp dt equals 0.693147p. This is more confusing for people, I think, than the difference equations. Remember, the difference equation we looked at was pn plus 1. It was 2 equal to 2pn. Here we got derivatives. That's one thing that makes it more difficult. And get this natural log in there. Weird. What in the world's going on? What's a solution? This is a solution. However, we almost never write it like that. We almost always write it with e, base e. Since 2 to the t is e to the ln of 2 to the t, right? Because 2 is e to the ln of 2. Did you ever realize that before? That is true, right? The e and the natural log cancel. Typically, you go the other direction. But I could go this way. I could say 2 is e to the natural log of 2. And then by a property of exponents, I can bring the t inside here and multiply right there. And the natural log of 2 is approximately 0.693147. So this 2 to the t is approximately this thing. That is an approximate solution of this differential equation. Why? Check that left-hand side equals right-hand side when we plug it in. I did that here. Let's do it over here. Let's go ahead and write it in exact form with the natural log of 2 in there instead of the approximate 0.693147. Y equals P0 e to the natural log of 2 times t power. Its derivative, dy dt. Now we have an e. By the chain rule, we're going to get an extra factor of natural log of 2. Right? The derivative of natural log of 2 times t, that's just a number times t, is natural log of 2. So that's what the left-hand side, LHS of the differential equation, simplifies to. What about the right-hand side of this differential equation right there? Natural log of 2 times p. Plug in, I probably should have called this p. Plug in this. P0 e to the natural log of 2 times t. That's what I did there. And hey, this equals this. Just the natural log of 2 is a different spot. These two things are the same. This is a solution of the differential equation. The left-hand side equals the right-hand side upon substitution. Can't emphasize enough how important that is at the beginning of this class to realize that. It seems more complicated. Why? Do we really want to do a differential equation instead of a difference equation? Yeah, there are plenty of reasons to keep going on differential equations. What is this? How do you interpret this natural log of 2 part in terms of what's called a continuous or instantaneous growth rate? As a percentage, the continuous instantaneous growth rate is about 69.3% per month. Because this, if you write it as a percentage, is about 69.3%. Graphically, what that means is exponential growth. If you're at any point and you make a tangent line at that point, the tangent line over 1 unit of time, from say t to t plus 1, the tangent line is going to grow by 69.3%. That's a 69.3% increase. And it doesn't matter what t is. Okay, that's what it means. The actual growth is more than 69.3% because the graph's concave up. And in fact, the actual growth is doubling. Going from here to here, the output actually has been doubled. It is still doubling every month for the rabbit population. But the instantaneous growth rate as a percentage, which I should really call a relative growth rate, I think I'll do that before I put this in the Google Drive, to change it to a relative growth rate, is about 69.3% per month. All right, here's some graphs similar to before, except now I connect the dots with the curve. There is the solution, P0 times 2 to the t, which is approximately 2 times e to the 0.693t. P0 is 2 here. Here it is on a bigger scale, and here it is on a logarithmic graph. Same kind of graphs as before, except now we connect the dots. With a smooth curve here and here, with a straight line here because it happens to be a logarithmic graph. Okay, once again, I'm doing this kind of weird stuff as a preview of lecture 2 when we start talking about changing coordinate systems. We're getting close to the end here, hang on. Let's think practically, let's compare the models. What are their strengths and weaknesses of discrete versus continuous? Discrete, the difference equation is, well, it's simple. It's a simple idea and a simple formula to find. No calculus needed, right? You don't need any calculus for the difference equation, where you just guess the answer by pattern recognition. It gives a whole number answer at every whole number input, at least for this example. For other examples, the inputs will still be whole numbers or integers, sometimes called natural numbers, but the outputs will not necessarily be. And in fact, if we allowed P0 to not necessarily be a whole number, then the outputs wouldn't have to be whole numbers. But the inputs are. But therefore, it misses estimates of the population between the whole number times. You know, what's the population at time 2.34 or whatever I said before? Couldn't I still use the same formula, though? Yeah, you could. But in terms of the difference equation, you want to pretend you don't. And there are good reasons for that, and we'll get into examples later. What about the continuous model differential equation? That's harder. Once you know calculus, it's fairly simple to represent and find, maybe. But if you don't know calculus, then you're kind of stuck. But, you know, if you're in this class, you should know calculus, so you are okay here. Gives an approximate population for all positive times t, including fractional, including even irrational values of t, like pi. Though you can't measure time so precisely. But we should always round the answer to a certain number of decimal places at least. It's not necessarily the nearest whole number, but we probably should round to at least the nearest 1 or 2 places after the decimal, typically. In both cases, you should realize they are approximations. They must always be tested against reality and tweaked or completely reworked if necessary. And probably for these rapid populations, this complete reworking is probably necessary, right? Unconstrained growth is just not practical. All right, here's a two-dimensional model, a predator-prey model. This is the second to last slide here. Just want to introduce this two-dimensional model. Consider a population of rabbits, R, and now foxes, F. Is this Zootopia? No, the foxes want to eat the rabbits. Assume the foxes, the predator, eat the rabbits, the prey. This is a predator-prey model. What would be a reasonable kind of assumption to make about what might happen when rabbits and foxes are interacting? When the rabbit and fox populations are high, the growth rate of the foxes should be positive and the growth rate of the rabbits should be negative. Why? Because if both populations are relatively high, at least if they're in a limited area, there could be a lot of interactions between rabbits and foxes, a lot of eating opportunities. And that's going to help the foxes to grow, positive growth rate, and make the rabbits die, a negative growth rate. You could call it a positive decay rate, would be the same as a negative growth rate. Conversely, when both populations are low, there's not many interactions, not many eating opportunities. The rabbits have free reign. The growth rate of the foxes should be negative, and the growth rate of the rabbits should be positive. Foxes don't have much food, they're dying off. Rabbits don't get eaten much, they are growing. What kind of basic model would satisfy those kind of conditions? We could even make such a model graphically without even thinking about differential equations, perhaps. And that's what I've got here. I've got rabbit and fox populations, predator, prey. Fox is the predator, rabbits is the prey. Now what do you see here? You see this oval shape, a red dot and a blue oval. What's going on here? Time is going by, that's time. There's your initial condition. F of 0 is 1.5, maybe 100 rabbits, which would be 150 rabbits, or foxes, excuse me. And at time 0, R is 2, maybe 2,000 rabbits. The units for the foxes and rabbits don't have to be the same. Maybe foxes are in hundreds of foxes and rabbits are in thousands of rabbits, or maybe even 100,000 rabbits. Where are these both high? They're both high over here. R and F are both high in that case. What's happening there? The foxes are growing, the point is moving to the right, and the rabbits are decreasing, the point is moving down. The growth rate of the foxes is positive, the growth rate of the rabbits is negative. On the other hand, when they're both low in value, over here, the point is moving up and to the left, this direction here. The rabbit population is growing because it's moving up. And the fox population is decaying, it's going down, it's moving to the left. Does it have to come back to where it started? No, it doesn't have to. In this particular model, that happened to be the case, based on the particular differential equations that I happen to choose here. The system of differential equations that involve derivatives now, not difference equations, and initial conditions, this is an initial value problem, is what I'm about to show you. It's there. Where did I come up with this? I just made it up. It is a common kind of thing to make up. df dt, the growth rate of the foxes, at any moment in time, you want to think of time as being in the background here, it's really important, equals, well, based on where you're at in this picture, this phase plane, what the coordinates of the red dot are at a certain fixed time, take the f coordinate and negate it, and then add the product of the r coordinate and f coordinate. The f coordinate is the first coordinate, the r coordinate is the second here. Whatever number that gives you, that's the rate of change of f with respect to t. So if r and f are both big, if you're over here, that product is going to be fairly big, and this is, this negative f's a negative number close to 0, perhaps, or closer to 0 than this is. So this is going to be a positive quantity, and df dt will be positive. And here, notice r times f is being subtracted. When r and f are both big, this is going to be subtracting a positive number. And this could be big, could be small. Well, maybe not as big as this, at least. Ultimately, possibly making this quantity negative, dr dt is negative. On the flip side, when you're over here where r and f are both small, then r times f will be small. You're adding a small positive number here, subtracting a small positive number here. Whereas these numbers could be further from 0. When they're small, df dt will be negative and dr dt would be positive. So the coefficients and their signs are the key thing to look at here. Negative coefficient there, positive here, negative there. Here's your initial values. Now, that's a pretty hard thing for people to understand at first. Don't worry, we'll spend plenty of time thinking about that as we go. What's the unique solution for this initial value problem? Can you guess it? Guess what? There is no simple formula for it. It's impossible. What? But didn't I graph it here? Yeah, I graphed it based on using a computer program that we will use sometimes called Mathematica. This is actually not from a formula. It's from a numerical approximation, which is essentially data. And just connecting the dots, the data dots, with a smooth curve. I'm making it continuous instead of discrete. This does not come from a formula, it comes from a numerical method. Now, Euler's method is probably not good enough to produce a nice curve like this. So it's a better method than Euler's method, but we'll look at Euler's method because it's simpler. It's a big theme. This is a nonlinear system. These are nonlinearities here. These two parts are linear, first powers of f and r. And the r and f both have first powers here, but you're multiplying them. So these are nonlinear equations. And in general, nonlinear equations, you can't find the solutions. But you can still understand what the solutions look like. And you can still interpret them with tools like technology like Mathematica or like phase plane analysis with these things called null-lines and linearization. Okay? Last slide. Bethel University is a Christian liberal arts school, and my students, I want to encourage you, but I also want to encourage anybody else who is dealing with difficulties during this pandemic especially. Trust in God, both in good times and hard times. And a couple verses that always come to mind for me here are Philippians 4, 6 through 7. This is the NIV version. Do not be anxious about anything, but in every situation, by prayer and petition means essentially asking with thanksgiving, thank God, both in good times and hard times. Present your request to God, and the peace of God, which transcends all understandings, will guard your hearts and minds in Christ Jesus. As a Christian, we believe in Jesus Christ, that He is God, and we believe we have a relationship with Him that goes through His Word and through prayer, or His Word being the Bible. And it's the peace of God and joy in both good times and hard times that is what God gifts you with when you have a relationship with Him. So just a prayer for my students and anybody else out there who feels like you need prayer. I am praying for you. Bless you, and I'll see you in lecture 2.